Well, welcome everybody. I know it's a little bit boisterous right now because there was an exam that went late in the room. So if we could just settle down, that'd be great. Okay, we've got quite a bit to cover today, and I hope that it'll be clear and interesting to you. Today, yes. Okay. For those who have extenuating circumstances, there are multiple people who approached me. Go ahead. All right, but I'll show up at the end for those who come in late. All right. All right. Let's go. Let's go. All right, so today we're going to continue our discussion on torsion, and in particular we're very focused on understanding what's happening with a shaft, okay, a circular cross section. Now you can do these types of problems with different types of cross sections, say rectangular or square, but the numbers or the math is not quite as clean, all right, and you can get some approximations, and I used to kind of focus on some things with non-circular cross sections, but at this point we're pretty much just concerned about circular cross sections. Okay, the math works out quite nicely. Now, in our past meeting, right, we discussed the torsion formula, and the torsion formula is that which we use to calculate the shear stress, right? And we've talked about how the maximum shear stress, hey guys, folks, thank you. All right, so the maximum shear stress is on the outer surface of a circular shaft that's being twisted. And then we have rho, which is a metric that we use for the radial distance from the center line of the shaft to be able to calculate what the shear stress might be inside that circular cross-section. Typically, unless you have a distributed torsional loading, which we'll cover today, what happens, right, is that you have sections where there's no additional external torque being applied, and so your torque is going to be constant across that section. And then, when we say, between point A and B, or between point B and C, whatever, right, we know that at least the internal torque that we calculate is usually constant there, unless, of course, it's distributed or there are other external loads between those 2 points. So really, when we're thinking about, hey, what's the shear stress at a particular location, we need to know something about, hey, is that being calculated at the outer surface, or is it being calculated at some inner location across that circular cross-section, okay? So today, we're going to talk a little bit about shear strain, and then be able to eventually get that to our angle of twist. Okay. We'll also go back to session 1 and revisit the relationships that we discussed between torque and radius for the amount of load that might be supported by a shaft. And then we'll do distributed torsional loading, we'll do indeterminate torsional loading, and we will also do some finite element analysis at the end, okay? I've cut some of the stuff. When I looked at the notes that I've presented previously, I realized, wow, this is a lot, okay? And I probably didn't do a very good job, quite honestly, in presenting some stuff. So hopefully today will be better, but also, some of the material that we covered in the previous lecture sessions, that material I'm going to reserve it for the extra videos for the assignments. Okay, so stuff on the gears and things like that. So you just have to get some of that information. You just have to watch the videos that I will attempt to post, by Monday. All right, so you have a little bit of time. All right, so some of the things we're going to talk about today, we're going to discuss, all right, The twisting of a shaft fixed between two walls. Yes, we're going to do that. Okay, we'll relate torsional load to diameter of a shaft. Yeah, or we'll be able to figure out, you know, what the shear stress is. And we already kind of done that actually. Angle of twist, that we should be able to do today as well. Normal stress is induced by torsional loading? No, we're not really. That's not something that we're going to concern ourselves in exploring, and it's quite low, quite frankly. Okay, but if you want, we can take a look at the FEA when we do it in the end, and you'll see that it's low relative to the shear stress. And then distributed torsional loading along a shaft, yes. Now, this graph, okay, or this sheet of notes, okay, is kind of a recollection of what we discussed, okay, plus a little bit more. So first, this is just our torsion formula, okay, saying if I want to know the shear stress, then I can use that torque, I can use that radius, and I can, if I know the polar moment of area, I'm good. This is Hooke's law. This is saying, all right, and we discussed this previously as well, so now we have an ability to divide essentially by G, okay, over here, to say, okay, that's going to be the shear strain. What is shear strain? Shear strain describes the amount of distortion we have. And we often think of it in terms of this angle that comes out of this parallelogram when you apply the shear stress to it. Okay? And another way, if you want to represent this with a matrix, and this is a very simple matrix, is that we could say, okay, tau xy is equal to, well, G times gamma xy, right? Just like that. So these are all those relationships. So what we're saying here, just like if you have uniaxial loading, right, and it's in the x direction, sigma x is equal to E epsilon x, right, if it's uniaxial loading. Okay? But remember, if you have those orthogonal normal stresses, that's going to affect the strain that you have in that desired direction. And we've kind of, okay, don't get scared, we've kind of already done half of this, right? This matrix, the top three of this column vector, okay, that's epsilon x, epsilon y, epsilon z, and these Poisson ratios, okay, and this 1 over e, and these normal stresses, and that's exactly, these are the relationships, right, that we described previously. We said we can write out, for example, that epsilon x is equal to 1 over e times this quantity sigma x minus nu times quantity sigma y plus sigma z, right? And so that's there. We can now go further, all right, and we can take the inverse of this matrix and multiply it against both sides to figure out what this would be in terms of the epsilon and the gammas, the epsilons and the gammas, right? Do you have to be able to do this? Probably not, okay, but is this good for your future in mechanics? Yes, probably, okay? So that you've seen these relationships, and we've seen how we can go back and forth between them, okay? So just like we were discussing with the uniaxial normal stresses, we can also think about, okay, that kind of tau xy is equal to g gamma xy, right? That's kind of in just saying, okay, we have shear stress operating kind of in one plane, okay? We can also have an expression that is more expansive, all right? So we can say, here's the gamma xy, all right? And we can say that we're going to have tau xy that affects that. We're going to have tau xy that affects it as well. And tau xy will be equal to this. So what's interesting here, right, is that unlike what we had with the Poisson ratio still has an effect here, actually. This Poisson ratio is actually the G, all right, or it affects the G. The E over 2 times quantity, 1 plus nu, that's G. That's the shear modulus, okay? And what's also interesting is that, you know, these shears in the other planes, if you will, okay, those are not going to be affecting say, so what's happening with tau xy does not happen, doesn't affect what happens in gamma xy. Right? That's a little bit of a unique behavior, right? We saw that here, okay, just like we have here, and we, I maybe was leading up incorrectly to say, oh, all right, well, if you have normal stresses in the other two directions, right, it affects what's happening with epsilon. Well, here it doesn't. Okay, gamma xy is only going to be dependent on the tau xy. It's not dependent on the tau xz and the tau yz. Any questions on this? I'm sorry, I might have gone. Yes, go ahead.
Can you explain again how the shear modulus works?
Okay, so the shear modulus, okay, is just like what we've been talking about for stress strain curves. Okay? Except it's the slope between the shear stress and the shear strain. Okay? So that's how it works. But it's a little bit confusing in that, the normal stress and the normal strain, right, they were kind of in the same direction. You can kind of see them more easily. What we're talking about here is that this, if we go back over here, right, we kind of already discussed this, I guess, right? We discussed how the shear strain, right, comes out of this derivation when we described it last time, right? And we said, hey, look, there's this triangle in here, and that's the angle, right? And what we're saying is that angle is proportional to the amount of shear stress, okay, that you have on that cross section. Does that help?
And the shear only applies by torsion, right?
Right. Right now. Okay. When we do beam bending in the future, we're going to talk about transverse shear stress. Okay, and that does not. It's not from a. It's not from this type of torsion. Okay. Good questions. Okay, so now remember this session 1. Okay, this is just to remind us why in the world do we care about shafts? Right, we're stepping back. Okay? Well, they're used in a lot of systems. Okay, a lot of systems, from your cars to manufacturing lines. Right, the Industrial Revolution was taking advantage of this, to your turbines, to your jet engines. Right, we see shafts in a lot of different places. Okay? And I don't know, has anyone ever had a failure with a shaft that they can recall? No? Okay. Maybe? Okay, well, let's do it again, right? Here. This is your failure, chalk. All right, now you've all seen, this is stronger than I am. Hold on. My hands are sweating. Oh, this is so embarrassing. There you go. All right. We'll talk more about why the shape looks like the way it does, right? But now you've all witnessed static failure of a shaft. All right, that's lame, right? But you get the idea. You don't want your shafts to fail, right? You don't want them to fail. And if you're in a vehicle that has wheels, this is going to be an issue, right? Even you can think of a bike. All right, so I came on a bike today, electric bike, right? Imagine I have a force from the chain, right, going onto my sprocket, okay, and then that's connected to a shaft. Now you're thinking, oh yeah, but the wheel just turns. Does it? Nope, not exactly, right? I had to have force in order to go forward, correct, right? And so there's got to be a force on that wheel, right? That's essentially providing my propulsion, okay? And there's going to be a reaction force on that wheel, and so there's going to be a load in between the sprocket, right? There's going to be a torsional load. The sprocket's going to want to go one way. The wheel's going to want to go the other way, right? And so that torsional load is going through the shaft. Okay, that's connecting the sprocket to my axle. Okay, car's the same way, right? You're like, oh, the car just goes. No, it doesn't just go. I mean, yes, it would better go, right? When you put gas, when you push the accelerator, right? But the point is that when you have a motor, when you have a power source, right, driving your wheels, it has to transfer that load, that power, right, through the shaft. And so even though it's spinning, and we're doing the static case where it's constant velocity spinning, right? So you got a torque, right, and you know that the power is equal to torque times omega now. You knew that before probably. But when you still have that torque that's being applied to that shaft, and that shaft is being twisted all the time. It's running. So we can figure out what the angular displacement, the angle of twist is, right? We can figure out what the stress is, the shear stress, right? And we can figure out if our shaft is going to be good enough. And the other place where you might find a shaft that's being twisted is in torsion bars. So if anyone has a nice truck, which I do not have, okay, you can adjust the the suspension by turning some things. I've never done it, okay, on your torsion bar, okay, and so you can adjust the height like that. If anyone has, what I have experience with is opening my trunk, okay, and the trunk, they often have torsion bars in them as well. That's why the trunk stays open, and that's why it's easy to open. Or often in DMC, I guess it's different this semester, but we also talk about kind of like these basement doors that you open, right? They often have a torsion bar in them as well to help you open that heavy panel. Okay, so they're in a lot of different places, not just but this is where you're going to see them the most as shafts. And then we've already gone through the types of materials that you have, right? And this is also from session 1, right? So what we said, does anybody remember what we said? That the scaling was between the diameter and the load, the supportable load? Yeah, Mark? Diameter cubed, right? Okay, so where does that come from? Where did this all come from? Well, it comes from, you're going to have what we'll call a SSY. Okay, what do you think SSY stands for? It's the shear strength at yield. Okay, so imagine now you've got a nice little space like this. In fact, let me just do this over here. I think I even made us. Yep, here we go. So you've got an SSY. This is the shear strength at yielding, or the yield shear strength, or whatever you want to call it. Okay, and if I look at this beautiful shear stress versus shear strain curve, right? What does this mean? This means if it's a linearly plastic, linear elastic, perfectly plastic material, okay, it's going to behave something like this, right? And so I can say, okay, this is going to be my kind of limit where it starts to yield, and I can also say that, if this is where it's going to start to yield, I don't have a, yes, but I don't want to do that. What happened? Okay, this is where oh, now it went blank, right? Okay, hold on. Let's see. Come back. Oh my goodness. Hold on. Come on. Come on, come on, come on. Okay. So this is the limit, right, where we get into a shear strain that is corresponding to yielding, right? So, you know, sometimes I call that epsilon y when I've got a normal loading type of situation, right? But this is for shear. So SSY, okay, that's going to be essentially the shear strength at yielding, just like that. So if we now plug in, or we think about our TCNJ formula, all right, the TC over J, what are we looking at? We're looking at, hey, what is the maximum torque, maybe, right, that would be associated with this SSY. So we're going to look at this relationship, and we know that, you know, this is, I guess I should say, this is tau max because I've used C there, right? That's the outer radius for the torsion formula, and J is equal to pi over 2 C to the 4th. So then what do I get? I get TC over and now we get 2T over pi C cubed. So that's where this relationship came from that we discussed in the first time in our first meeting. And it says something important, that if I want to decrease the amount of shear stress that my selected material is experiencing, I have two options. One is to design my system to have less torque. Okay, so maybe I've got my, I choose my ratio of teeth on my sprockets so that I only get to a certain amount of anticipated torque, right? I'm gonna say I'm gonna have more rotation, okay, to be able to have a smaller torque, maybe, right? But if you're also designing, you just look at what the diameter of it is, and you increase the diameter, by a modest amount, and you're going to get a significant increase, okay, in the supportable shear stress. Okay. Any questions? We're good on that, right? Yes.
Are screws considered shafts?
Okay, yeah. So in design, I keep saying this, right? In design of mechanical components, you will talk about screws, and you will talk about tightening them appropriately with torques and the pretension that's involved. So the screws are interesting in that they experience both a normal stress, okay, because they are clamping together plates usually, right? They're holding two things together, and that's normal. So they experience a normal stress, and then they also experience the tightening. So you have a torque that you're loading on them, okay? And so that's and then they also have stress concentrations because the teeth or the grooves, okay, the threads. Sorry, what am I talking about? The threads in the screws also have kind of sharp curvature to them, and so that can increase the effective stress, especially under fatigue-based systems. Right? Stress concentrations usually, and you'll cover this in DMC. Stress concentration is just a fancy way of saying corner. Internal corner that causes a higher stress than you anticipate. Okay? So you try to avoid sharp corners. But in reality, for most problems with static loading, that is not a huge problem. You don't have to think about the stress concentration factor too much. And we're doing static, so we're happy, right? But when you have fatigue, then you do have to consider that, or impact. You will be more concerned about these correction factors. Anyway, that'll be next semester. Okay, so let's look at some relative deformation, okay, with angle of twist. We talked last time about how this phi, all right, this angle of twist, would be proportional to the length. Okay, so we said that, right? And you could think of phi, if it's halfway along this shaft, it's going to be half what it is at the end, right? So 1/2 phi of L over, or 1/2 phi of L is equal to the phi of L over 2, for example. Okay. Now, we also have derived this relationship. This is with the pizzas and the slice of pizza from a notable Rutgers pizza place, okay, on the table in the office. Just jog your memory with lots of good toppings on it. We derived that we could relate shear strain to this rho times d phi dz, okay, and this d phi dz, right, that would be the slope, right? So if I know, this is of course a derivative, right, but I can given that this is a linear relationship, if I know the angle of rotation at this end, I know the length, right, I can just pop that into d phi dz, right, that's the slope. We can rewrite d phi like this, right? This is just rearranging these parameters. And then we now bring in our Hooke's law again. So tau equals g gamma. And we can then rearrange or substitute, right? This is gamma goes in here. Okay, so we get d phi equals tau over g dz over rho. And we have the torsion formula, which tells us something about the shear stress and torque. That's important. You combine them. You see where this is going? All right. We have a d phi over here. We have a dz over here. All right. What does this mean? It means that with this expression, we can integrate both sides. Okay. Like that. And immediately, what does this expression remind you of? Yes. Yeah, it reminds you of the integral for P that we use for PL over EA, right? Except this is with torque. Good. Your name is? Okay. Okay, chat. Okay. All right, so, Chet. Okay, great, Chet. Okay, so we can now write out kind of the equivalent, the exact equivalent of Fleet or Pli, right? PL over EA, as 5L is equal to TL over JG. Once again, we highlight, well, it's a rhetorical question. Is T internal or external load? It's once again going to be the internal torque. Okay? But it's, of course, related to the external torques that are being applied to the system. Okay? So it's just very analogous to Pli. All right? And yes, you can say that torque could depend on Z, J could depend on Z, G could depend on Z. Right? You could do all these types of things, and the analogous equation is, like Chet just said, the integral of P over EA with respect to X, usually, or with respect to Z in this case. Any questions on this? So now you have the power to go around and look at shafts. Right? Before, we established the superpower of looking at structures and being like, oh yeah, that thing is under its own weight, so it's got to be deflecting a little bit. Right? And I think most of us got a little bit of experience about that on Tuesday, being able to calculate that out, what gravity does to structures, right? And so this is kind of similar. Now you're like, oh, if I start spinning on one of these chairs and I am applying some torque, even though I'm slipping, right, but there's some torque there, I can think about, hey, what's that little bit of angle of rotation that I have? Okay, that in the shaft that I'm supporting myself on as I twist. Or, how much strain am I putting my body through, right? What's my angle of twist? Okay, just in the static loading when I stretch. All right, so there are all these types of analogies that we can think about. Okay. All right, and then again, we can define a KT. Aren't you excited? We can define another stiffness, right? Instead of the K that we had, right, which is right here, which is EA over L for a bar. Okay, we can also think of taking this equation, manipulating it, and it's just JG over L. Again, you see, these analogies are just running so nice and parallel with each other. The problem is that, well, at least for me, I think that twisting is harder to, right? I mean, why do we teach force equilibrium in physics before we teach equilibrium with the moments, right? It's because, well, it's a little harder to get your grasp on, to understand. Okay, so constituent relationship relating torque applied to a shaft with the angle of twist is the following, okay? Well, this would be, right, this would be shear stress. This would be J. This would be shear stress. This actually is a quantity called I, right, the second moment of area, which we'll talk about in a little bit when we get into beams. So the only one, this is the only one that gives us the, that relationship for the angle of twist. All right, now, what if you have multiple regions? Well, we can say that the angle, and this is essentially sum of local angles of the twist. I'm going to say for shafts in series. Okay. Why am I saying that? Why is this for shafts in series? And you can kind of see this drawing that came up too. What do I mean by that? Someone, describe it. What are we talking about when we say phi is equal to the summation of these angles of twist? Yes? Yeah, right? So this one is going to twist. Oh, where is it going to crash on me? Ah, oh, come on. Okay, I'm sorry. It's well, actually, okay. Good. It's still working, right? Great. So, what's your name? Nick. Okay, so Nick, what Nick is saying is, look, I put a torsional load on this end, okay, and then both shafts twist. There's going to be some angle of twist for the first region, and there's going to be another angle of twist for the second region, and the total angle of twist at this end is going to be equal to the phi 1 plus the phi 2. And I can write it out. Okay, so this is analogous, right, to springs in series for normal loading, right? Because if I have a spring like this, right, and I want to say, oh, hey, what's the deformation of this one? Delta 1. And what's the deformation of this one? Delta 2. And what's the deformation at the end? Delta, right? I know that the delta is going to equal to delta 1 plus delta 2. Right? So that's the relationship for displacement. What's the relationship for the internal force with springs in series? Yes, Mark. It's the same, right? It's the same force in both of these springs. What's the deal here? Through equilibrium, the torque is also going to be the same in both regions. Okay? And you could have different stiffnesses, right? So these could be different shapes. Okay? Just like these could be different springs with different spring constants, or they could have different diameters or different cross-sectional areas. These two bars, if they are. Okay? But the torque is going to be the same. The internal torque is going to be the same in both when they're in series. So this is just kind of rehashing this out. Okay. All right. Now, What is this? This relationship, though, is a little bit weird. Okay, this is describing something that's a little bit different. Okay, this is actually describing two shafts in parallel. What do two shafts in parallel look like? So we now have an idea of what two shafts in series look like, but what do two shafts in parallel look like? Yes?
Would it be the rotation in the middle of two shafts, so that like you have rotation of the two shafts separately, like it's fighting against?
Okay, all right. So yeah, so that so they're good, right? So one way of looking at it, okay, as Brennan was saying here, is if I had these shafts like this, and I'm applying the torque here, okay? If I do that, right, just, what does this look like? This looks like the bar, right, stuck between two different members, right? So this is going to have, the torque is not necessarily the same in these, okay? Because that's an external torque being applied there in the middle, right? So I have some reaction torque here and some reaction torque. So the torques are not going to be the same, right? But the displacements are the same. And so since the displacements are the same, okay, then this is going to be in parallel, right? So this is series, this is parallel. Okay? I'm sorry, it's getting a little bit messy. I also had a mechanics professor who kind of wrote all over the board. Anyway, so now I'm doing the same thing. Sorry, okay? Okay, but this is going to be true for either case, right? That we can have a torsional spring constant. Okay. Now, what's another way you could draw two shafts in parallel? What was that? Two shafts in parallel. Yes?
It'd be like when you have like two bars and you have two shafts in between them and you try to twist the two sides.
Okay. I think I get what you're saying, right? Another case. Okay, I need another case for another case. Okay, would be something that kind of looks like this. Okay, so what I've got here, this is all material where I've hashed, and maybe there's a gap. You see that? Okay, so what's happening, again, both of these are going to experience the same angle of rotation, right? If they're so essentially what I'm saying is concentric, right? So you have one maybe solid shaft in the middle, and then you have a hollow shaft that goes around the solid shaft, and that they would be experiencing the same displacement. The torques could be different. Okay, so that's another way to think about parallel. Okay, so just ways to approach this. Now, one thing I didn't cover too much, and I probably should, is how do you calculate, so if you're going to do TC over J, right, or you're going to do TL over JG, right, both of these have J in them. Okay, both of them have J. So how do you calculate the J when you have a hollow cross-section, a hollow circular cross-section? Any suggestions? How do you calculate What do you think? Yes.
I looked this up earlier, so it's pi over 2 times the c to the 4th power minus the inner radius.
Right. Okay, so if I have a hollow cylinder, and you can do the math out. I think I used to do the math out, maybe. But you can think of how, so this is the solid where I've crossed, right? And we'll call this C1, and we'll call that C2. Okay. You can think of it as, oh, I'm losing some of my material, right? It's not resisting as much. And fortunately, right, so the integral that you're trying to solve, all right, is the integral of rho squared dA. Okay, that's the that does make it look a little bit better, right? This is the integral that you're trying to solve. And when you do this out, okay, there's no material in here, or there could be a different material inside that could be, fun, I guess. But you have this idea that, okay, they're going to add. Okay, they're going to add, the spring constants add when they're in parallel, because these two things are in parallel with each other. So, like, is it Jonathan?
Yes.
Yeah, Jonathan was saying, right, when you solve this integral out, you get pi over 2, we'll call it C2 to the 4th minus C1. Okay. And that's how that's how you handle the hollow cylinders. Okay, those are some assignments. We haven't gone through how to do all this. I'm going to generate videos, okay, so that it will be clear how to do these problems. Okay, this problem also I'll generate a video for, but I don't want you to get too scared. I just want to talk about this for a second because we're going to do the finite element analysis that is for this problem in a little bit. This problem involves a geared system, okay, and it involves wheels. Yes, this is really as primitive as I can probably get with 3D CAD. And the structure that I'm concerned about failing is this this shaft, okay, going between, let's say, the drivetrain and the wheel. This is a simplification, but you've got a drive axle, right? So you have your transmission, right? Then you've got a drive axle often going to your differentials, and then going to other shafts, right? The axle is going to your wheels. Anyway, this could be part of one of these systems, okay? And so what we're saying is there's a force, right, that is the wheels are exerting on the ground, or the ground is exerting on the wheels, okay, as the vehicle is moving, and that generates a torque, right? That generates a torque, and then that torque, like we've talked about previously, right, is being transferred through the shaft and then going up into the drivetrain, into the transmission of the vehicle. Okay? And so the question would be, what diameter? So the question could be there could be a couple of different questions, but one question could be, what is the shear stress that you're generating in that shaft? Or what is the diameter that you have to design that shaft to be so that I don't have failure? So we'll do some examples in finite element where we show how we calculate the stress, the shear stress in that shaft. Any questions? Okay, now, our friend, distributed loading. Okay, so what are the units for a distributed torsional load? A lowercase t, analogous to lowercase f. Okay. Well, they are going to be torque per length, or Newton meters per meter, or weirdly, newtons. But it's okay, you can write it as Newton meters per meter, right? And what is this? This is like a little t that's being applied along the shaft. And if you look in past exams, I guess maybe, Jumbo the elephant is not the most realistic character, okay? But what I said in one of them is that Jumbo has the ability to put its trunk around a shaft and twist it, and is somehow magically then applying a distributed torsional load, okay? All right. You could think of other systems that are maybe a little bit more realistic. We're not going to do capstans, but sometimes people in mechanics do capstans. Capstans are just essentially a shaft that is put in place, for example, for holding a boat, where you wrap the rope around it, okay, and then it holds that line taut. And that's based on some exponential and some friction between the two, okay? Or you could think of, a cable-driven system where you're winding up a cable. So these might be some systems that are maybe more realistic than an elephant deciding that it wants to twist your leg off of you or something like that, okay? So the inner rule that we use is saying that, okay, I've got some distributed torsional load, okay, T, distributed torsion, right? And I do TdZ, I do the integral of that, and that gives me a TL. And, if I'm only going a certain region into that, and now your brains are like, oh, I remember something very similar to this. There's an analogy to this in normal loading, right? I only go a certain distance, then I only need to integrate up to that distance. And it's the same relationship. Instead of TL, it's just TZ, whatever distance I'm going up. Right. Okay. Now, let's say that I have my shaft connected to the wall. And I've got a distributed torsional load like this, and it has some length. Well, remember, if you have a bar hanging from the ceiling, right? What is the reaction force? Well, the reaction force of the ceiling holding up that bar is just, we're talking about bars, we just went to normal loading, right? If I have a bar, how do I calculate the amount of force that I have to hold it from the ceiling? Yes, Chet. Yeah, you need the length of the bar, yes. You need the weight. Yeah, you want the weight of the bar, just the weight of the bar, right? So it's mg, or it's rho times the volume times g, right? That's what that reaction force is. So this is analogous in that it's just the total torque, and it's just TL, right? And if I had a lowercase f and I was doing that, gravity thing, right? What is the lowercase f for a bar, right? We're just talking with our hands, and we're just, doing things for fun. But what is the lowercase f if you have gravity acting on a bar? Yeah, rho g area, right? Exactly. Okay. So this is that's nice that we have gravity doing this. This is going to be the I'm not going to be able to tell you. I'm trying to think of how I just have like a natural system. I guess I would have to have, like, you could imagine. Okay, here's a natural system. You could have like a shaft with like a bunch of weights hanging from it, okay? Where you have, and then that would be some way to have gravity naturally twisting a bar, okay, with a distributed load. Yeah. Okay, I would have to have like a continuous log here, okay, and then we could say, okay, that's the distributed torque, right? And that would be, like essentially mg, right? The total, whatever this would be mg, right? And then I've got it over some length, and I've got it acting at some radius, right? We use c because we use c a lot in this class. So that torsional load up here. Let me just brag. I really am becoming like this person. Anyway, this would just be the mgc, right, divided by L. That would be like a distributed load. I mean, like, I don't know. Now I'm thinking of analogies. Like, you throw your clothes on the shower rod, right? That's kind of like applying a distributed torque across it. Right. Anyway. So but that's not how your curtain works, right? Your curtain has got little rings, and that is applying a very nice normal load. Okay, that's a distributed force. Okay, that's going across it, because you could say that's acting, right along the center line. And we'll talk about that if you want to. This is the first time I'm coming up with problems for shower curtains and shower and rods, but whatever. You got the idea, right? So, and that would be beam bending. That will definitely be a beam bending problem. So here, if we look at the external equilibrium on the system, we have a reaction torque. All right, we just shifted gears again. So we have a reaction torque, and we have this distributed torque. And they balance out so that the reaction torque has to be equal to TL. Okay? So that's like step one, do external equilibrium. Internal equilibrium is a little trickier, right? So of course you can choose, I could choose, and often, right, when we did the windmill, the windmill spinning blade, right, and we were looking at the distributed force, I thought it was easier to think about it in terms of, because that was a centrifugal load, right? So definitely easier to think about it from the outside moving in, because I didn't need to know the reaction force from the get-go, or I didn't need to calculate it out. Or if I have a hanging bar, it can also be easier, right? Because then when I'm doing my slices, all right, I don't need to know what the reaction force is from the ceiling acting on the system. Okay. So here we do balance, right? We have an internal torque, and notice that internal torque is following our convention. What is our convention? That if we have a surface, a face, right? So if it's, am I going the same direction as this? No, this is the same direction. All right, if I'm going the same direction, right? I've got my face, and this is going to be the torque coming out. So I'm going to define my internal torque to be positive coming out of that face. All right, and so then I've got this positive torque, and the way I've drawn my little t, it's the same direction, but TR is in the opposite direction, right? So now, using internal equilibrium, we can say that the internal torque is equal to this T times quantity L minus Z. Okay. And if I want to figure out the angle of twist because of this, then I get to do this integral of 0 to L, right, of the internal torque over JG. Fortunately, J and G are staying constant, and then we have this expression like that. And remember, this is actually, I mean, this is a little bit familiar, right? Because we were talking about how we had when we had a bar, right? It was like the rho G L squared over 2E, right? So this is kind of analogous to that. Except we have a J here. So in the case of the hanging bar, because of the way that force, that distributed force was working, right? It was rho GA. The areas canceled out, so we didn't have an area dependence. Okay, here we have a J dependence. But depending on how you would define your T, it's possible that the J dependence could pop out. Any questions on this? Okay, so now we've done distributed torsional loading. Fun. Okay. What about indeterminate? So what is the definition of indeterminacy in statics? What is the definition? When we say we have an indeterminate static system, what does that mean? Yes. Okay, well that's what we often think of, yes, that it looks like it's fixed between two walls. All right? Can we go a little more technical or a little bit more general in our description? Yes, you want to? What's that? Right, so when we did it with normal forces, there were more unknown parameters for the forces than we had equations to solve them, right? Just using statics. So what did that mean that we had to do? It means we had to, yes, Chet? Okay, we had to use geometric compatibility, yes, and Mark? Okay, so we have internal equilibrium. Actually, so internal equilibrium, if it's a determinate problem, you can use only equilibrium, right? But we're talking if we have an indeterminate problem, we have to use more than just equilibrium. What else are we going to use? We said equilibrium. We said geometric compatibility. Yeah. Huh? Constitutive, right? That you have to use your constitutive relationships. And I know that's what you were going to say. Don't worry. So, so you have to use your constitutive relationships. And those constitutive relationships, what do they essentially do? Those are the ones that relate the loading to deformation, right? That was the missing piece in statics last semester, and that we've introduced this semester. Okay? So when we say we have an indeterminate torsional system, or we have any indeterminate system, right, what we're saying is that we have to go beyond just equilibrium, and we have to use, yes, geometric compatibility, that's true, and we really need constitutive equations. Okay? We need equations that can relate loads to displacements, loads to, displacements either angular or linear, or we need some type of relationship that can relate, stresses and strains to each other. Okay. So for torsional systems, and yes, O'Colors, then like what did you said at the right here? Okay, I lost you, but that's okay. Like our friend here was saying, it's often between two walls. Yes, your name is Stephen. Okay, so statically indeterminate torsion. Equations of equilibrium are insufficient to determine the torsional loadings. Okay. So what does this look like? It looks like something like this, okay? And we already did this. When we talked about it, right? We said, hey, this is like two springs in parallel, right? Okay. We can say, there's an internal torque, TA, all right, which would be equal to the reaction torque, okay, from the wall. There's an internal torque, internal torque TAB is how we usually call it, all right? And that's equal to TA, which is the torque at the wall. There's an internal torque TBC, which is equal to TC, which is at the wall. And if we do the external equilibrium, okay, we have the following, and then we can do the internal equilibrium. So this is where we get the TA is equal to the TAB, like this. And we can say that these relationships are true and that we have TAB equal to TA. And we can say on the other side, we have a TBC, which is going to be equal to TC, right? Or negative, of it, okay? But we're still kind of stuck, right? We're still stuck. We have not enough equations. We have not enough equations to figure out what's happening. So what we have to do, okay, is go a little bit deeper. So we can use geometric compatibility, for example. And so the end-to-end twist, okay, angle, all right, what is that going to be? So we're talking C relative to A. Yes. Yeah, it's going to be 0, right? Okay. It's also going to be equal to what? It's also going to be equal to, okay, the deformation that you have, in this region, plus the deformation that you have in this region, right? Or you can say, right, and this is equal to 0. Or, so you add them together and it's equal to 0, or you say, hey, they're twisting in the opposite directions, okay, right? They're in equal magnitude. So now we bring in the constitutive relationships. And here, right, we can say that the angle of twist, if I know, what the internal torque is, all right, I can figure out what the angle of twist is going to be, because that's going to be TL over JG. Okay. And of course, this is true on the other side as well. And so we can say that angle of twist between B and C is going to be that TBC, LBC over JG. Okay. And now we're seeing, oh, hey, we've got some relationships here we can use with our geometric compatibility. We had equilibrium already. Okay. And we can combine these equations and get the following. Okay, I'm going fast. Go ahead. Okay. All right, so, yes, maybe I went too fast there. All right, so this relationship, right, is for the angle, the total angle we said, right, which is 0. And these were the individual displacements, the angular displacements, the twists of the left and the right, okay, or this is the right and the left, okay? These were the equilibrium equations that we had. And then we can say that when we plug these things in together, all right, that we're going to be able to solve for either TC, TA, right, TBC, TAB as well, all right, and then we can figure out what the torques on the walls are. Okay. Questions? I mean, I know I went fast through that, but do we see an analogy here to, again, the normal loading types of systems? Yeah, right? And we have this idea that if I want to know what the torque is, okay, let me, in fact, let me just write this. This might be kind of interesting too. Okay, so here's a relationship. First off, let's just explain what this is saying. This is saying that between, if I have these two, like this, and let's say this is LAB over here, and this is LBC over here, and I'm interested in the TC. There's a torque here on this side. There's a torque here at this side. Okay. You probably haven't seen this before. I don't think I've described it like this before to you, but what we're saying is that TC is going to be equal to the torque times the ratio of this length divided by the entire length. So if LAB is really big, really long, okay, relative to the entire thing, that means that the reaction torque here is going to be very close to whatever the torque is. Because that's suggesting that this side has a very low stiffness. Okay, it just will go with the flow, right? So if I have a TC that is about equal to the torque that's applied to the system, this is saying that right, this is C, this is B, this is A, this is the LAB, right? It's saying that this is really large relative to this. Okay? And so the TC, the torque over here, in this little sub-region, right, that internal torque also is essentially taking the whole load. Whatever is being applied at this section T, at this intersection, that torque, it's essentially going all into the wall. Okay, this is like a springy mess, right? Because it's got a lot of length. What I'm feeling that I should have told you before, and what I'm telling you now, is that this is true for bars as well. Okay. So that as we make a bar that might look like something like this, if I apply this force here, and I'm interested in the reaction force, okay, Fc. This is actually going to be going this direction, Fa, all right, that this, because this is so long, all right, the Fc is also going to be, and I'm applying a force here, also going to be Lb over L. And also Fa is going to be F times LBc over L. And this equation, if I say that I have a KAB and I have a KBC, right? We already talked about this a little bit, but this is essentially saying, look, this is going to be the ratio of, is this right? Now I'm getting, yeah, this is KBC over K, affect the total K times, yeah, just like that. Okay, and K total would be I just did this on the fly. All right, so I think that's right, and actually it's on the exam. So that's how you can think of these systems. All right. Any questions on this? Okay. In fact, I think I did that. I think I did that wrong. I think this is okay. I had to double check. I'm not going to check here, but this is either K total or it's K. No, that's. I think that's yeah. That's right. Okay. Any questions on this? Okay, so the ratio of these lengths affects the the stiffness, right? And it affects the amount of load that these different members are going to be supporting. Now, okay, this we're going to skip. Okay, this for that I'll go through and stuff. Okay, I got 10 minutes. You can stand up and just watch if you want. Take a breather. I'm going to go through. I'm going to try to go through in 10 minutes how we can simulate a shaft in torsion in FreeCAD and PreProMax. Okay. So this is just the shaft, for example, in this system. There's a force given, there's a length given, and there is a torque associated with that force times the radius of this wheel. If I apply this torque on one end, then it's got to be applied equally and opposite on the other end to keep it in equilibrium. We expect that this shaft will twist. Our objective with doing finite element analysis is to figure out what the shear stress is and what is the shear strain. So let me go ahead and bring up FreeCAD. And we're going to make a shaft. Now the shaft has length 1 meter, has elastic modulus of steel, 200, and it has a Poisson ratio of 0.3, and it has a radius of 3 centimeters. So we're going to create a new part. We're going to go ahead and use the part bench, workbench. We're going to use a cylinder. We're going to change the radius so that it's 3 centimeters, so that's 30 millimeters. And the height is going to be 1,000 millimeters, just like that. Okay? And so there it is. Okay? That's our shaft. We're going to export that. And we'll call it, sure, unnamed cylinder is fine. I don't mind that. Okay, and then we're going to open up okay, our downloads. Okay, where I have PrePoMax sitting. We're going to open up PrePoMax, and we're going to import that geometry. So that geometry will come into a new model, like you see here. We'll call unnamed cylinder, just like that. This, once again, you remember how when we bring things in, often PrePoMax is using different units when it looks at STL files. This is not supposed to be 1,000 meters. It's supposed to be 1 meter in length. So we come to geometry, we go to transform, we go to scale, and then we're going to bring it down. Okay, apply, like this. Okay, it looks like it disappeared, but we can zoom in, and it's just like that. We can move downward in our work. So let's do a mesh. We'll create the mesh parameters. We're going to do this on the part. Okay, and I've done this a little bit. We're going to make the smallest about 8 millimeters. Okay, or the largest, sorry, the max element size will be about 8 millimeters, and we can go ahead and we can create the mesh just like this. Okay, and that's not a bad looking mesh. You know, maybe it's not the best mesh, but it's not bad. Right? You can see how since we're discretizing a curved surface, okay, with non-curved lines, right, we lose some fidelity to that curved surface, and so that's something that you have to balance whenever you do finite element analysis. All right, we're going to go ahead and we're going to find a surface on the right side. Here, this is where we're going to end up applying our torque. We're going to create a reference point on this right side as well. And this length was 1 meter, so we'll just put it here, 1 meter. Okay, there's a reference point, and this is centered on 0, 0, or on the 0 line, right? So we have x, y, or 0. We have the opportunity to define a material. We're going to define an elastic material. And we said it was something like steel, so 200 gigapascals. And we said we'd use a Poisson ratio of 0.3. We are going to define a solid section for the entire geometry. Okay, that's important or necessary. Maybe is a better way to say it. Okay, click on it. Okay, that's in there. We got a reference point, we got a surface. Yes, we're going to tie the reference point to the surface and make it rigid. Okay, and this we're going to use this surface name. Surface 1 has already been defined, so there it is. And then we're going to go ahead and jump into doing our physics, which is going to be a static physics model again. We hit OK. We can go ahead and we can define our boundary condition for this side. So we're going to create, and we're going to do fixed. We're going to do surface. Oh, okay. Oh, I twisted around. Good. Okay, and that'll be okay, and that's in there. I'm going to move things over here a little bit. The load, we're going to apply a moment, not a concentrated force, but a moment. And it's asking where. We're going to do it to our selection, which is the reference point. And if we go here, the load we're supposed to apply is not in the x direction, not in the y direction, but it's in the z direction. So that z direction, right, it's twisting it like that. That z direction, we said it was 1150 Newton meters. Just like this. Okay, and now we see that there's a little torque, a nice torque applied there. Okay. All right, if I didn't do anything wrong, if I did things correctly, we should be able to run. It will take maybe 6 seconds on this computer to run. Okay, 8 seconds, probably because it's running other things too. We look at the results, click on the results, Ah, looks kind of pretty. Roy G. Biv. Anyway. But anyway, okay, that's not what we care about. What do we care about? Well, this is where it's important to have a little bit of a concept of what shear stress is. Now remember, it has two subscripts, tau. We have, and remember that these subscripts can be flipped, okay? But usually what we say is the first subscript is going to be the face, and the second subscript is going to be the direction. Okay? So the faces that we're going to be interested in looking at shear stress, which faces, if you had to think about this, which face? Remember the diagrams for shear stress? Okay, if we go back over here, which face? Go all the way back to the very beginning. There we go. That's it. Okay, which face are we looking at for shear stress? Coming at you, right? So that would be the Z face. Okay. Which directions are we looking? So if it was in the Z face in the Z direction, that would be a normal stress, right? Right? Yeah, exactly. So we're thinking X or Y. All right, and this is where it gets a little bit tricky, okay? Because X or Y, okay, so I've got this face and I've got my X and my Y, and my shoulders are bad. Okay, but I'll use my hands, right? So I got this face coming out, I've got X or Y. My max stress is going to be when my stress that I'm calculating is in the same direction as one of the coordinate systems. All right, either the X direction or the Y direction. So what does that mean? That means that, okay, if this is Z, and let's just say that this was an X-axis and that this was a Y-axis. All right, let's just say, all right, that if we had this as our X, oh, that's really bad, and this is our Y, that's really bad, right? Then I would say, okay, the stress is maximum out there, right? But there's other stress. The shear stress is radial, okay? If I go to one of these other locations, it's not going to be as high because the stress is not acting, right, in, for example, 100% the Y direction, right? That's what it would be acting at here, or 100% the X direction, or the negative X direction, which is what it would be acting here. Is that clear? This is an important point, right? That you're going to get maximum stresses, shear stresses, when you're on on either the X or the Y axis, based on how it's handling the coordinate, how we're handling our coordinate systems. Radially, it would all be in the theta direction. Okay, that would be the circumferential direction. But because we're in Cartesian coordinates, we have to be very careful about where we pick our stress analysis. Okay. Quickly, because we're out of time, and then of course I will make a video for this to describe it. Let's look at S13. So S11 is not useful, S22 is not, S33, no. S12 not really either, because that doesn't involve a Z direction. So I got to look at S13 and S23. So let's look at S13, all right? And what do we see? We see that it goes in these interesting bands. And if I pick a geometry, a view, okay, let's say top view. Okay, look at this. This is in the X direction. Remember, we're doing 1, 3. This is X to the right, Z is this way. So if I think of this system, all right, as like this is kind of like, the Y, if this would be kind of coming out Y, I do a query here, and I select this spot, okay? What do I get? I get a stress that's like 250 something megapascals. All right, it's negative because it's going the other direction. And if I go back, okay, to my slides, you'll see that it was about 257 megapascals is what I calculated. Right? There are some nuances that I'll talk about in the video between the shear strains, and the that you calculate by hand, and the tensorial strains that pre-pull max uses. So there's a factor of 2 between them, but that will come out in the videos. So, where is it? Oh, sorry, not 200 and, it's 10 to the 7th. It's not 250, it's 25 or 20, it's like 25.6 megapascals. My bad. So that's 27.1 megapascals is what we calculate. So we're in the right ballpark. Thank you, everybody. I will see you on Tuesday. There's quite a bit to this assignment, okay? I'll be honest, but I'm going to provide the videos, and good luck getting through the questions, okay? If you have questions, send messages in the group me. Have a good weekend.